we start with the revision of solutions. Then I'll discuss something called colligative properties or collective properties because of solute in solvent, and we'll also discuss one very important type of model to describe solid solutions or liquid solutions or different types of solutions. It can be gas mixture also, and these are called quasi-chemical models. So we'll go into that, and we'll also discuss colligative properties. So initially, in fact, I'll start with real solutions again. So I'll emphasize, so before I go to quasi-chemical models or colligative properties, we'll briefly recollect real means ideal versus real solutions. So as we know, in ideal dilute solutions, for example, we know that there is this solvent, which, so dilute solution means where the concentration of solute, say B is the solute, then XB tends to 0, and XA, that is the solvent, tends to, and we also have seen, so basically the amount of solute tends to, so amount of solute, we can write this way, solute, so solute concentration tends to 0 and solvent tends to a pure solute. So concentration tends to 1, right? So in this case, solvent obeys Raoult's law, but the solute, so solvent obeys Raoult's law and solute obeys Henry's law. So this is some, although it is an ideal dilute solution and we are talking about Raoult's law, so Raoult's law is something that is obeyed by the components in an ideal solution. For example, if you have an AB binary solution, then AA, that is the activity of A or apparent concentration of A, equals to XA. And even for the other component, we can write AB equal to XB. But here, for solute, it is not Raoult's law, but Henry's law. So we will see what does this mean. So what does this mean? AA equals to XA and AB equal to gamma 0, XP where gamma 0 or KH is the Henry's law coefficient, right? And this is drawn basically as XB tends to 0, right? As XB tends to 0. So if you look at the plot, the gamma 0 is obtained, or the slope is obtained by drawing a tangent to this curve or to this where XB tends to 0. Okay. So if I look at a real solution, for example, a mixture of acetone and chloroform, which we have discussed in the earlier class, you see this is the concentration of chloroform, and as a function of concentration, the partial pressure of chloroform is given by the partial vapor pressure of chloroform is given by 0, 4.7, 11, 18.9, 26.7 and 26.4. It is increasing. So as you increase chloroform, the vapor pressure due to chloroform is increasing from 0 to 36.4 kilopascal. On the other hand, that for acetone goes from 46.3 when there is 0 chloroform, that is pure acetone. The vapor pressure reduces to 0 when acetone becomes very, very small. Now, if you plot that, you see neither it's not following any law, neither Raoult's or Henry's law. Basically, as you can see, if you look at, it's a function of C. So this is XC. There is a mole fraction or atomic fraction of chloroform. So chloroform is 1.0 here, and this is basically acetone. This is basically acetone. Right, this is A, and XA goes the other way, right to left. So XA increases from right to left, while XC increases from left to right. And you can see the point. If you follow my line, then you can see that there is deviation from ideality, right? There is deviation from ideality here as well as from in here. So this is basically for, this is from A to C. As you can see, A to C, there is an increase in vapor pressure. So A to C, as you go to POC, there is an increase. So this basically corresponds to PC, right? So PC 0 to 1, there is a monotonic increase in the pressure. But if you see the increase in the pressure, you look at the increase in the pressure, the vapor pressure, you see that it is not following a straight line, because this is P and this is XC. If Raoult's law would have been followed, then P A should have been PA star XA, and PA star is nothing but the slope, or PC equals to PC star XC. So that is PC star is nothing but the slope, and you see it's a straight line, but it is definitely not. If you join these points, it's definitely not a straight line. So it is deviating or there is a departure from Raoult's law. But if you want to use Raoult's law, then you can basically, for either A or C, you can start from here and you can draw this yellow line here. So this is for C. So this is for C, which is PC equals to PC star XC. And what you basically get is nothing but the slope is basically here PC star. So for this yellow line, you see the slope is PC star. Okay. While for this yellow line, for the other line, that is for acetone, you see there is a decreasing trend, right? There is a decrease in pressure. From pure acetone, it is going to 0 towards pure chloroform. So basically the slope is minus PA star. Now how do you basically tell? So if you look at PA equals to PA star XA, so the slope is basically minus PA star. If you look at this line, so the slope is negative, right? It's minus PA star. So if you can see, it is plotted against XC. So PA star minus into XA is nothing but PA star into 1 minus XC. So basically PA star, so minus PA star XC, as you can see, and then there is also an intercept. So minus PA star XC, and the intercept is basically PA star. So this is basically PA star. This point is basically PA star. PA star is the vapor pressure of the pure solvent. So this is PA star, and this is nothing but PC star, right? And the slope is minus PA star for acetone, because for acid, the way we have plotted, XC increases from left to right, and therefore for acetone, the vapor pressure continuously decreases from pure acetone to pure chloroform, right? Now, if we look at Henry's law, what we are doing, Henry's law is basically giving you, so for any component is basically PC equals to gamma C0 XC when limit XC tends to 0, right? XC tends to 0. So if you look at for chloroform, you will basically draw a tangent to this white curve that you have interpolated curve through the data point. So you have these data points. If you look at this data points, you have this data point, this data point, this and this, and this guy and this guy. Now if you look at this, is a curve. This is a curve, right? This is basically, as you can see here, this white line is a curve. Now for this curve, in the limit XC tends to 0 is here, right, at the origin here. So because here A equal to 1, that means acetone is 1, therefore chloroform is 0. So at this point, if you now draw a tangent to the curve at X equal to 0, you are drawing a tangent to the curve. Now that tangent line gives you the value of gamma C0, which comes out to be 22.0 kPa. So gamma C0 is 22.0 kilopascal for chloroform. Similarly, for acetone, we will go to the chloroform end where acetone is 0, and we will draw this curve, we will again draw this green line, which is a tangent at this point, at the limiting point of XA tends to 0, and where it meets the y-axis, and that value is like 23.3 kPa, and for acetone that means the Henry's law coefficient is 23.3. Correct? And as you know, the partial pressures are basically measured in this way, that you have PO2, this 21 So this is basically partial pressure of oxygen dissolved in water at 25 degrees Celsius. You have PO2, which is 21 kilopascal, and if I give you Henry's law constant, that is basically kilopascal kg per mole. Okay, this is kilopascal kg per mole. Then basically you can also use, basically what I am trying to say here, this example tells you that you can express Henry's law in terms of molality. That is, molality means amount of solute per 1000 grams or per kg of the solvent. So Pb equals to KBBB. So Bb is basically nothing but molality. And if you know BO2, that is the molality of oxygen, you basically can find out if you know KO2, which is it is basically 7.9 10 power 4 kilopascal kg per mole. So BO2 comes out to be 2.9 in 10 minus 4 moles per kg. That means it's a very small amount of moles per kg, right? Per kg of the solvent, right? Or per kg of the, sometimes you can call it per kg of the solution. But I think, strictly speaking, the molality is per kg of the solvent. So basically now, so if you look at that, if I know BO2, then O2, the concentration per unit volume of O2, right? So the in moles per unit volume, the concentration is BO2, that is molality, times rho water, right? So as you can see, this kg is per solvent. So basically BO2 times rho water, which gives you 0.29 millimoles per liter of water solvent, right? 0.29. So the amount of oxygen dissolved at 25 degrees Celsius from what is given, we find out to be it is 0.29 millimoles per liter, right? Now, in an ideal solution, all this Raoult's law is followed by ideal solutions. And see, this is the partial pressure form of Raoult's law, but the Raoult's law can also be expressed in terms of activity, and we already know the way it is done. We write activity of a component equals to gamma A XA, where gamma A is the activity coefficient, and if gamma A equal to 1, then basically this is nothing but Raoult's law for component A, right? So this is something we know. So if it's gamma A equal to 1. So for ideal solutions, gamma A should be equal to 1. So if you look at a binary solution, for example, mu A star, say for example you have mu A star, mu A star is nothing but the chemical potential of pure A, chemical combustion of A in pure state. Okay, so there is a star that indicates it's a pure state, but this is equal to, we can write that this is equal to the standard state. The pure state can often be taken as the standard state or reference state. Similarly for B, you can take the pure B, that is the mu B star, to be the reference state or the standard state, right? Now, if you think of this, the partial molar free energy of A, so basically please note that partial molar free energy of A in the pure state is equal to partial molar, so in this case, partial molar free energy of A in the pure state is equal to partial molar free energy of A in the reference state, which is nothing but, remember, partial molar free energy is nothing but the chemical potential, right? So that is chemical potential of A in the pure state, and that is chemical potential of A in the standard state. So the pure state can often be taken as the standard state. That's the only thing that I wanted to tell you. So you can also choose a standard state that is not the pure state of either A or B, but it is also convenient to choose the pure state for A or for B to be the standard state. So now let us look at mixing. So if you look at mixing, what happens? So mixing is what? We have some moles of A, we have some container containing A, and we have some container containing B. You have A, some amount of A, and some amount of B, and you are mixing them together, right? That's the idea. So you have a container which is like A, which contains, so I'll just draw that. A molecules, A, and plus you have another container which contains B, and you are mixing them together. okay, to form. So now before you mix them together, what do you have? You practically have, say let us consider the atoms of A to be red. So you have some A atoms here. You can see there are some A atoms, and say consider so this is basically, so we tell this is basically B, this is basically A, then I am adding them together. So the initial state is basically what? I have pure A, I have pure B, and so the initial state before mixing is Gi superscript I, basically indicates initial, is equals to nothing but, as we have shown before, it is Na times mu A 0. This comes from what? It comes from the Euler equation. It's a standard Euler equation at a given temperature and pressure. At a given temperature and pressure, at a given T and P, at given T comma P, you can write Gi, that is the initial, the free energy of the initial state of this mixture of A and B. This is just before mixing, right? We have still A atoms, the block of A atoms, and we have the block of B atoms. We haven't mixed them. So you basically have the total energy, but we have just taken them together. We have just brought them together, but we haven't mixed them, right? It has not mixed. It has been just brought together, okay? Then think of this like, imagine this like A atoms, a block of A atoms and a block of B atoms are put together, are coming together to form two subsystems, and they are basically subdivided by a partition, and this partition is not yet removed, so that A and B are basically, we are not allowing A and B to mix, okay, and that partition is basically impermeable to either A or B, okay. Now then Gi, that is the energy of the mixture, the total energy of the mixture will be, the free energy of the mixture will be Na mu A 0 plus Nb mu B 0, where mu A 0 and mu B 0 are basically the partial molar free energies or chemical potentials of A or B in their pure state, right? However, after mixing, what happens? After mixing, you basically get Na mu A. So as you can see, Na mu A plus Nb mu B, where mu A is the chemical potential of A after mixing. So when it has been mixed, so what does it mean? How does it look like? It looks like this. So you have some A atoms, and then you have some B atoms at random, B atoms, A atoms at random, and say some. Like that. So you basically have made a mixture, a completely random mixture of A and B, and what you get is basically, so Na times mu A, the Euler equation becomes Na times mu A, where mu A is the chemical potential of pure component A in the solution. So this is basically not the component A in the pure state, not mu A 0, but mu A, and mu A is nothing but the chemical potential of component A in the solution, right? Chemical potential of component A in the solution. Similarly, because they have formed the solution, and Nb times mu B, where mu B is the chemical potential of component B in the solution. Now this is after mixing. Now as you know that mu A can be expressed as mu A 0 plus RTLN AA, where AA is the activity of A, right, of component A. Similarly, mu B is mu B 0, mu B 0, mu A 0 are in the pure state or standard state chemical potential, and then there is this additional term, right? There is this additional term. So this is something that you please concentrate on, like RTLNAA and RTLNAB, and this AA and AB, we call them activities of A and B respectively. Now, for ideal case, AA equals to XA and AB equals to XB, that we know. Now, GF is Na mu A, right? Instead of mu A, I am writing mu A 0 plus RTLN XA, and NB mu B 0 plus RTLN XB, and delta G mix is nothing but GF, G final minus G initial, the free energy of the final configuration minus free energy of the initial configuration, which comes out to be NA-RT-ln-XA plus NB-RT-ln-XB. Now I can write NA is nothing but N times XA, and NB is nothing but N times XB. N is the total number of molecules or total number of atoms, right? So in such a case, you get N XA RT ln XA plus N XB RT ln XB, or you get N RT XA ln XA plus XB ln XB. Okay. So basically delta G mix becomes N RT XA ln XA plus XB ln XB. When you have an ideal solution, that is what you get. So you basically get delta Gm mix, which is delta G mix by N. That is, this is the molar free energy of mixing equals to RT, right? Because it's divided by N. N is the total number of molecules or total number of atoms. Then basically this becomes RT XA ln XA plus XB ln XB, where N is the total number of molecules or total number of moles of. So basically the total energy of mixing is this, right? And where N is the total is the mole number of compounds, right? N basically is the mole number of mixed, is the total mole number of components N, or in other words, N is nothing but Na plus Nb, where Na is the mole number of A, and Nb is the mole number of. Now, so delta Gm mix, that is the molar, right? Because I am now divided by the total number of moles. Total number of moles is N, right? Total number of moles is N. So I am dividing by that. So I get the molar free energy of mixing, which is RT XLN XA plus XB and XB. And for a solution with C components, I can generalize. So this is for binary, two components, right? Instead of binary, we are talking about C. C is the number of components. Okay. So then, if C is the number of components, here I equals to, basically here I equal to A and B, right? Or 1, 2. So basically it's x1 ln x1 plus x2 ln x2, or 1 minus x ln 1 minus x plus x ln x, where x is basically the mole fraction of set B. Okay. But if it's a solution with C components, a multi-component solution, then delta Gm mix, that is the free energy, the molar free energy of mixing equals to RT times I equal to 1 to C xi ln x. Right? This looks very familiar, right? Xi ln xi. You have already seen that, right? Delta Sm mix I have told that is nothing but it is minus R xi ln xi. Right? I don't want to repeat again, but what I am trying to say is that once you know delta Gm mix, you can basically get delta Sm mix, you can basically get delta Hm mix, which is equal to 0, right? For an ideal solution, right? Delta Hm mix equal to 0. Remember, in many books, instead of ideal, a term perfect is used, and sometimes perfect seems more appropriate than ideal, because in a perfect solution, what we assume is that there is no interaction between the constituent atoms of different kinds. So basically, if you have A, B and C making a solution, and the solution is basically perfect, then basically A, B and C, they do not interact. A means it seems to A that it is occupying the entire volume, or it seems to B also it is occupying the entire volume, and to C also that it is occupying the entire volume, because A, B and C, they do not mutually interact, right? In a perfect solution. However, in an ideal solution, the interactions balance out. I'll come to that. I'll soon come to that. But what I am trying to say, I am just recollecting here, delta Sm mix ideal is this, delta Gm mix ideal comes out to be delta Gm mix plus T delta Sm mix, and delta Sm mix is minus R xi ln xi, which is basically positive, right? Which is basically positive. So now that is so, delta Gm mix is delta Gm mix, which is RT xi ln xi plus T delta Sm mix, and delta Sm mix is minus R xi ln xi, and we multiply with T. So delta Hm mix as the enthalpy of mixing for an ideal or a perfect solution where there is no interaction between the different kinds of atoms or different kinds of molecules is basically zero, right? So the enthalpy of mixing is basically zero for an even ideal solution or a perfect solution. Even the same goes for molar volume, right? We have already seen that molar volume of mixing, right? Or the molar volume of mixing is basically del delta G del P, and del delta G del P in this case is equal to 0. Now comes real solution. So this is where the difference is. Now look at the initial form. The initial form does not change. The initial part does not change. This does not change. However, the final part, look at the final part. Now instead of writing XA, I am writing activity of it. And here also I am writing activity. But as we know that AA equals to gamma AXA and AB equals to gamma BXA, where gamma A is the activity coefficient of A and gamma B is the activity coefficient of B, and they are not equal to 1. Now in that case you have A naught T. So if you look at the delta G is nothing but again GF minus GI, which is equal to GF minus G. GI is nothing but Na. So in GI, what are the terms involved? Na mu is 0 and Nb mu is 0. Okay, now all of these are gone. So you have Na RTL and AA plus Nb RTL and AB. Or we can write N common, NRT, XAL and AA plus XBL and AB, and then you can write this as NRT, XL and gamma A, because AA is gamma XA, right? XL and gamma A plus XL and XA, and X and again XB times. So this is all within the bracket. So basically, I will just tell you, this is all with the bracket. So basically XL and gamma A. So basically this what I am writing here is instead of XL and gamma A, I am writing XL and AA, I am writing XL and gamma A, which is equals to XA ln XA plus XA ln gamma, right? So that's what I am doing. So XL and gamma A, XL and XA, XBL and gamma B, XBL and X, right? Multiplied with NRT. So if you do that, so NRT, this term XL and XA plus XBL and XB comes, and then there is this term, right? This additional term comes in. Now as you know, delta GM mix real is equals to, so again the molar free energy of mixing for a real solution is nothing but the delta G mixer is the total free energy of mixing for the real solution divided by the total mole number, right? So now this becomes RT XL and XA plus XB and XB plus RT. So as you can see, there is this additional term, right, in the real solution, XL and gamma A plus XB and gamma. So basically, if I now just look at this part, this is the ideal part. So delta GM mix for a real solution is a sum of delta GM mix of the ideal solution plus delta GM mix excess. See, this is the most important concept that you learned in solution. So basically, as you can see here, when you are looking at a real solution, there is a part which is also the ideal, means that we have proved that RT, XL and XA plus XB and XB is nothing but the free energy of mixing for an ideal solution, right? Free energy of mixing for an ideal solution. However, this term, okay, RT equal to XL and gamma A plus XB and gamma B, this is basically, as you can see here, this is basically delta GM mix excess. Please note the superscript. So delta GM mix excess is delta GM mix real minus delta GM mix ideal, and delta SM mix excess is delta SM mix real minus delta SM mix ideal. Now comes delta HM mix excess, which is delta HM mix real minus delta HMX ideal. This part, as you have seen, is 0. So this delta HMX excess is nothing but delta HMX. And this delta HMX here is nothing but the delta HM, or the change in molar enthalpy of mixing, that is observed. Okay, due to, why do you observe this? This non-zero value. This is due to AA, BB and AB interactions in a binary solution. If you consider a binary solution, then there are AA, BB and AB interactions. If this is a ternary solution, you have AA, BB, CC, AC, BC and AB interactions, right? That's the idea. Again, for delta SM mix excess, I can do that. Delta SM mix real minus delta SM mix ideal, and delta SM mix real minus of minus R epsilon xi, and then basically we can assume that delta SM mix real is nothing but delta SM mix ideal. So that means delta SM mix excess is equal to 0. Now, if you tell that delta SM mix real is the same as delta SM mix ideal, then basically what you are getting is minus R epsilon xi, right? Minus R epsilon xi. And if you plot this for a binary solution, you will see that it will have the highest. It will have the highest value at 0.5, right? At 0.5 axis, and this highest value corresponds to nearly 6, right? So this the highest value corresponds to ln. It comes out to be ln2 multiplied by R, right? So 8.314 multiplied by ln2, which is like 0.693, and basically what you get is very close to value very close to 6. So yeah, 8.314 and ln2 is you please check. So you will get a value very close to 6, and this is basically delta SM mix ideal, which is basically in joules per mole Kelvin. And as you can see, the ideal entropy of mixing has a peak corresponding to x equal to 0.5, right? X equal to 0.5. Now we'll go to one kind of real solution, which is called a regular solution. Now in that case, for a regular solution, we basically use a form given by this. Delta HM mix excess is nothing but H. There is a small h RT xi. Now this small h RT xj basically comes here. So this is not equal to 0, right? That was there for ideal solutions. So for real solutions, in particular for regular solutions, you can assume pairwise interactions, and you can basically write the excess enthalpy of mixing to be H, the small h RT xi, right? Now, if you look at this, a binary solution, let us first consider the binary solution. So as you can see, delta HM mix is already given as HTXXB, but delta SM mix excess, as we saw in the previous slide, that delta SM mix real is nothing but the delta SM mix ideal, and as a result, delta SM mix excess goes to 0. But delta SM mix ideal is basically minus R epsilon x. Now, if that is so, now you have delta GM mix, you have delta GM mix, and you have delta HM mix, you have delta HM mix. So delta G is nothing but delta H minus T delta L. So you have this delta HM mix, and you have T delta SM mix, and now this is nothing but, so as you can see, this is delta HM mix excess minus T delta SM mix ideal, right? This is the regular solution model, where the excess is only in the mixing enthalpy but not in the mixing entropy. Now if you do that, then basically you get H RT XXB, right? Small h RT, because that's what we started with, and plus RT excellent. That is basically what you are telling is this guy is the same as this one, and this part is the same, right? Now, if I just divide by RT, in this case, we get H times XXB plus XLN XA plus XB and XB, which is H1 minus XB into XB, and plus, so if you just do this manipulation here, so basically I am taking XB as the independent variable and XA plus XB, remember. 2, okay. Now, if I want to plot this for different values of H, this is what I get. So I'll discuss further in the next lecture. Okay, we will continue from here in the next lecture.